Welcome everybody to our webinar, Thermal Management Challenges in Medical Equipment. Our speaker today will be Dr. Kaveh Azar. He is the founder and CEO of Advanced Thermal Solutions.
Greetings everybody, this is Kaveh Azar from Advanced Thermal Solutions. It's a delight to be in front of you again via the electronic medium. What I'm going to be talking about is the thermal management challenges that we have in medical equipment. As we all know, the whole world has gotten quite a bit electronized, and medical industry certainly leading the pack because of the processing power and the imaging, etc., that goes on. That is very, very important. And as a result of it, thermal management is becoming a key parameter in designing these equipment successfully to make sure that they're functioning properly. So let's start with the the fundamentals and the basics and see whether we can just march our way towards the top and get to the nuts and bolts of the thermal management. And what I'm going to do is, after some introduction about the thermal management issues and so forth, we're going to go through a real example that we've done to show what the challenges are in the problems are and how similar they are between medical equipment and other equipment that we see in the electronics industry. So the first and foremost is, what is thermal management? We keep on hearing about thermal management, thermal issues, etc., etc. The process is very simple. There's a junction that is residing on this device, or multiple junctions for that matter, and that's a junction that needs to be at a certain temperature. In a sort of a topical type of impression, it is like a fuse, the old-fashioned fuses or circuit breakers that gets to a certain temperature and the fuse lets go because of the fact there is current crowding and the temperature increases. This junction effectively is the metallic interlayers that resides under the chip, and it could be the variety of locations or different chips or in the multi-chip modules and so forth, and that temperature has to be below a certain limit. Beyond that, it could cause all kinds of issues, as we're going to see in a short order. So you can see the liquid crystal imaging of these dyes that we've done with our ThermView system to see what the temperature gradients are. Obviously, in the liquid crystal thermography, you see the actual colors versus the manifested colors that you see in IR. So the whole notion is to make sure that the junction that we have is remaining below a certain limit that is set by the device manufacturer, and that really puts the essence of thermal management, electronics cooling all in one scope. If you don't walk away with anything else from this webinar and take one bit of information, and that's the junction temperature management. Electronics cooling is pivoting around junction temperature, not the approach air temperature to the device, not the air temperature of the system or temperature on the board, etc., etc. It's the junction temperature of the device that we have to manage. So differences in the medical industry that we see and what they are and why do we have to do it is to ensure that the device temperature, T sub J, stays below a set limit, to ensure the instruments or fluid temperature is isothermal, and to ensure fluid temperature is quickly cycled, meaning we don't want to have any kind of a thermal crowding taking place where the cooling is required, and also to remove heat from the miniature surgical tools that is essential in any kind of a medical application that we have. And one of the big issues, for instance, when you see in an imaging system, the system being isothermal, you're talking about something like in 2.5 meters with half a degree C, the requirement for temperature to be isothermal. These are major challenges that our brothers and sisters in mechanical engineers in these companies are working with in order to make sure that these criteria that I've listed here are met on a regular basis. As a result of it, we are dealing with effective equipment. You got to remember, at the end of this is not a consumer electronic type of a thing. You're dealing with human life and human related issues. So the level of precision and the level of control that has to go into the medical electronics and subsequently the thermal management is of huge concern and a point of challenge for all of us. Some of the unique thermal challenges that we see in the medical applications are stringent material selection. Copper may cause, for instance, tissue irritation or neurodegenerative conditions, spatial constraints, constant repeatability and temperature uniformity, and also meeting FDA requirements. And I mentioned about this because this is sort of near and dear to our hearts on the applications that we've dealt with, because smallest temperature variations in a given application, as you're going to see in the cell biology that we're going to talk about, it could kill the live cells, and your sample that you've very preciously generated or collected is of no use because of the fact that temperature could not be controlled. So these are the major challenges that we are confronting and we have to face and manage and learn how to work with it. And certainly it is important for us to be able to cognizant of those. General applications of medical equipment are quite broad. We have stationary like EKG machines and ultrasound and MRIs. This should be MRI, not MIR. Handheld like defibrillators and forceps and so forth. Biotech research, tissue and DNA. Again, there's an awful lot of work taking place in this area, where not only they're worrying about the thermal management, but also dedicated computers are being put together in order to do the biotech research and be able to do DNA analysis and so forth. Some of those computers that we've dabbled into before and worked and helped some of these companies to build, the thermal challenges are quite severe because of the fact the intensity of the computing that takes place. But at the end of it becomes electronics that we have to deal with and make sure that's working properly. So the factors that lead into the thermal challenges are very, very important. Unquestioned reliability. I mean, this is not something that we can take it in any shape or fashion. We have to make sure that the system is reliable. Instruments with greater accuracy and capabilities. We are dealing with very small, especially small areas or samples. Imagine somebody's taking an X-ray or MRI and so forth, and they need to go to the micro level in order to be able to decipher that. And any kind of electronic error manifestation that we see as a result of temperature could cause deviations. For instance, imagine you've taken an X-ray of your chest, and oftentimes the radiologists are not at the same location where the X-ray is being taken and is being communicated. If the communication device that sends the image and or the X-ray device that took the image have thermal issues, you could put impressions on the X-ray where the radiologist may misunderstand it as a tumor, as a growth, or whatever you want to characterize it as. Reduced size and miniaturization is huge. Patient comfort and dealing with small samples is a major challenge. And despite of medical costs going up higher and higher and higher, like any other section of the market, cost constraints is always huge, and we have to be able to design and put systems together that the electronics equipment manufacturers can be successful in selling and making a business and continue to develop the products that we need in our hospitals and at the doctor's offices and so forth. So let's take a look at a couple of examples of medical equipment and what they have to go through. As an example is a diagnostic imaging, X-ray or MRI, ultrasound, CAT scan type of system. Temperature fluctuations can impact accuracy and calibration. And again, pay attention to the words accuracy and calibration. Repeatability must be over 95%. We are dealing with human factors, and we cannot risk the chance of having errors as a result of our equipment not functioning properly. High heat load between 500 to 1,000 watt, and this is actually increasing like any other thing because of the rapid processing. And with low temperature limits, noise must be limited. A lot of patients get very agitated with these large equipment going around them, and they get claustrophobic, or they get nervous about, if any of you have done any kind of MRI ever, I've done a couple of them, there's a constant pounding sound that goes on because of the magnets being charged and discharged, and that could be a point of concern for some patients. Machine interface with patients must be taken into account. From the thermal standpoint, this is very important because no surface can be more than 40 degrees C, at the most 41 or 42. And anything over 42 is a red flag. Most equipment, the manufacturers, they try to make sure that their equipment is below 40 degrees C as a comfort temperature for the patient. And again, you've been to doctors' offices or hospitals and so forth, your temperature, pressure, etc. are taken, and your equipment cannot be too hot or causes discomfort or possibly skin burn. Sample analysis and screening, as I mentioned before, is very huge. There's a tremendous amount of push taking place across the country. We know the centers, for instance, for biological, like Massachusetts, Maryland, Texas, certainly California, as Utah, another state that there's a lot of focus in biotech type of stuff. So these are automated body fluid analysis machines, typically use optical or laser-based scanners cooled with TEC or heat pipes. Again, these are some of you who work in the electronics market. You're familiar with the TEC, thermoelectric cooler or Peltier device, and heat pipes that are excellent thermal transport tools. Not a cooling solution, but a heat transport capability. The temperature must be tightly controlled to ensure accuracy and also the integrity of the samples that we're dealing with. Heat pipes and vapor chambers are often used to ensure isothermal boundaries in order to make sure that we don't have temperature spikes. Imagine in a sample bed like this, if you have a significant temperature gradient, that some of these cells that are located here could potentially be affected adversely. So as we go through the design, as I mentioned to you earlier on the effectively 2.5 meters, half a degree temperature gradient, it's a significant and major milestone that we have to achieve when we go through the design. So thermal transport equipment like heat pipes or vapor chambers that spread the heat more effectively versus the solid conductor are used extensively for these applications. Biotechnology research is another area. DNA replicator must cycle between precise temperatures to promote cycle times are in the fraction of a second. Tissue research requires uniformity across sample and then repeatability. I need to be able to, if I discovered something, go back to my equipment and make sure my equipment is repeatable. Any kind of thermal fluctuations, any kind of temperature gradients and so forth across these things is going to cause havoc for the researcher. And the researchers are not engineers. They're using the equipment that we've designed to be used for their research and hopefully come up with parameters that could help human factors. So when we put this together, you can see that there is a great deal of similarity between what we see in the traditional or more commonly envisioned electronics market and the biomedical. Thermal management in medical field shares same common challenges with the telecom. There's extraordinary parallels or datacom that we see. Oftentimes you see in the background, you may not see it readily when you go to a lab or a doctor's office, but you see equipment like this that are residing someplace in the bodies of the chassis that's behind or somewhere in the hospital that to collect, analyze, convey this data going back and forth. So data transmission, data collection, manipulation of the data that requires CPUs or GPUs or DSPs, FPGAs, just name it. Standard stuff that we see in the other parts of the electronics market, such as telecom and datacom, are seen also in the medical. Medical devices have a need for isothermal or cyclic temperatures not found in other fields. This is a very, I think I've emphasized this maybe several times in the past few minutes. This is a really important thing that we have to focus on. If we don't pay attention to this, we're going to have problems in our equipment. And this comes management of the isothermality of it or not having cyclic temperatures. It really stems from the design of these. If my electronics are not designed in a proper fashion, from the thermal management and mechanical packaging standpoint, I am going to have those fluctuations and I'm going to have those challenges. And packaging and human interactions constraints are unique to the medical industry. And as I mentioned before, we cannot have something that's going to cause skin irritation, something that's going to potentially feel very cold or very hot to the human skin. And that's an area that it's very difficult. From the thermal standpoint, what are the challenges? I have a box that, for instance, the surface temperature of this unit cannot exceed more than 40 degrees C. And this is for the worst possible ambient. The ambient could be somewhere in a hospital or in a military field in a desert that air conditioning is not available. So my ambient temperature could range from, say, the typical hospital ambient of about 25 degrees C to something like 50 degrees C. So you can see that here I have about a 10-degree delta. Here I have 15-degree delta, 15-degree delta to manage. And this is a lot easier to work with than this constraint. But when I'm building this system, I don't know which one of these is going to go to. I have to design for the worst possible ambient. And as a result of it, the thermal challenge, taking the heat away from the surfaces and being able to discharge it in the equipment or in the air in the back of the unit or put it into the cooling system of the building, all become a part of the design process that we have to go through. Hence, we need to know the deployment site for the equipment that's going to be is going to be released and designed. That is really, really important, as we've talked about in other webinars. When we go through thermal design of any kind of electronic system, we always start from the ambient and go all the way down to the device. So we start from the ambient, where the system is going to reside, the deployment site, and we're going to go to the chassis. We're going to go to the board, and then we're going to come to the component here for junction temperature level management. This is where the junction temperature is managed, the T sub J. So this is quite a challenge that we have to go through, and as I mentioned, in the electronic equipment, this constraint of a surface temperature and also the human factor becomes a major point of contention and also point of analysis for us. So let's take a look at the case study. I think the best way to go through this webinar and give you a sort of a sense of what are the applications that people are seeing in the biomedical and how it's approached and solved, to give you a sense of what happens. Here's a project that we were involved with the tissue analyzer project. Problem is a long-term temperature control needed to ensure accuracy and repeatability. Again, remember, these two parameters surface themselves in the design process. The OCT, optimum cutting temperature, I'm not going to remember this again, so please remember that OCT refers to as optimum cutting temperature, is embedded for the embedded sample. Simple embedding process, troublesome array process due to heating of the OCT medium, and that's really important because excess temperature of the OCT is going to cause the cell to be damaged. Damaged cell is of no utility to the researcher. Solution is to frozen tissue microarray with sample cooling system as a example of managing this thing. So if I can reduce the temperature to a level that the tissue is maintained at a certain temperature for the duration that they're required without damaging the tissue, I have hopefully achieved the objective of this study. So the design goals are create a cooling system to maintain the frozen tissue sample below -70 degrees C for 6 hours. So you can see what the rigid constraint that is. We need to retain and maintain that for 6 hours at that -70 degrees C. Ensure operative visibility of the sample, so they can interrogate visually whether the sample is intact or not, or they have to stop the process and redo the samples. Eliminate humidity within our system to prevent frost buildup on samples and on components. The frost buildup is going to change the heat transfer from the equipment and also could adversely impact the sample and also block the visibility. So we need to make sure that the humidity is managed in an effective fashion in order to design to be successful for the given application. So this is Harvard Medical School's frozen tissue microarray that they have, and we got involved in redesigning this. And the final design looks like what you see here, and we're going to go through the bits and pieces of it and see what we had to do. This looks like not a very elegant cutting machine or stirring machine, as you see. It's no different. You have to have fluids that you have to stir and so forth. But the nugget is in here and in the design of these passages and so forth to ensure that the flow of air is separated. The temperature is maintained at -70 degrees for 6 hours. That's the tissue life. So for the design of the cooling system is convection cooling. We got a duct, we have a diffuser, we have a desiccant to remove the humidity, we have an air mover, a fan, and a heat sink. On the conduction side, we have the cassette that we have to manage, cassette receiver, As you can see here, this is the receiver. Insulation material to isolate the slurry, and dry ice and ethanol alcohol slurry in order to reduce the temperature to minus 70 degrees C. So this I call it a contraption that looks very much like a heat sink, is inversely put into the slurry here, and by cooling these fins, we are able to maintain the cassette temperature at a proper level. But there is airflow and also heat exchange that has to take place in order to make sure that's happening. The desiccants that you see here are put in the purpose of extracting the humidity out of the air. And remember, one of the conditions that we had was no humidity. The humidity factor was the one that we had to be able to minimize. And the way to minimize it, you can obviously run a dryer at the noise and the cost, but desiccants work very effectively, and the cost was also an issue that we had to manage. So the conduction aspect of it, you see the CAD model of the system. You have the cassettes that are going into this carrier or cassette receivers, and it looks like a heat sink that's going to go into the slurry, where a slurry is flown here. And the drawings that you saw earlier that showed how the convection is taking place are shown here. So double wall design for thermal resistance and holding the insulation. Extended fin design for constant thermal contact to make sure that we have very good heat transfer in the opposite direction to extract it from the cassette, or keeping the cassette receiver at the constant temperature, and tight fit between receiver and the cassette for heat transfer, in order to make sure that there are very little leakage of the fluid. When you're dealing with a minus 70 and a room ambient of 25 degrees C, you have about almost 100 degree delta T. That the temperature that every time I have a delta T, I'm going to have heat transfer, both on the conduction side, likely on the convection side, depending upon how the system is designed, and equally as important that a lot of us tend to ignore is on the radiation side. So I could have significant radiation heat transfer happening here as a result of this huge delta T, and it's going to impact my design. So I have to be cognizant of this as I go through the design in order to make sure that we've done this properly and we have not missed a beat. So we did some of the reservoir of it. We did some thermal analysis and testing, and you can see the thermal model of this using ANSYS software. We saw that by going through the simulation, the transient simulation, we were able to maintain the critical temperature for 9.75 hours with no insulation. And the total heat gain into the system was about 11 watts of power that went in there. So for the longest time, we could see that for almost 10 hours, we are able to maintain this temperature at the level that is exceeding the design requirements of minus 70. We were at minus 80 degrees C. So this showed that the design concept that we had is satisfactory, is acceptable, and we can march forward with the rest of it. The next one was a cassette receiver, and the intent was to see whether this is going to meet our requirement. Remember, the top of the cassette is open partially to the ambient, and we needed to make sure that thing is taken care of. Our initial model, no fluid flow analysis, just purely on the conduction side. We saw that the delta T of about 2.6 degrees C, and the thermal resistance equations that corroborate that is about 1.37 degrees C. So we are at the point that it seems like for the worst case scenario, we're going to meet the thermal requirements that is given by the design, and the design approach is correct. And then the next one was the OCT and the fin temperature difference that we wanted to make sure that that's at the level that is suitable. And we see that the OCT in this location, and the fin bottom is in this location. So you can see it on the picture here, where we made a sample to make sure that the design meets our expected requirement. And we see about a 2.5 degrees C temperature difference, which is very satisfactory. And note that the temperature is minus 70 degrees C. Our design requirement was 70 degrees C for 6 hours. So when we put the whole system together, we have the diffuser for the fan, where we have to have the airflow. we have the fan that in this location, we have the reservoir, and we have the heat exchanger on the sides to be able to extract this heat and put it out into the room ambient. And for the heat exchanger, you can see that we had to obviously use a fan, and we used the Sanyo ACE 40 fan, which gave us about a reliability testing. It was done at minus 80 degrees C and seemed to be satisfactory. It has a high output because of the fact it's got dual fans, and with a very good pressure drop. It's unfortunately a little bit noisy, but for the cooling standpoint and the requirement that we had at minus 70 with 7 or 6 hours of operation, we had no choice but to go with a fan that is going to meet the pressure drop requirement. And then on the design of the heat exchanger, you can see that there is a longer fin where the airflow is going out, and then shorter fins on the back side where it was inserted into the slurry here to be able to cool it effectively. And the fans were used to move the air through the upper portion of the heatsink. This is all made out of one piece in order to mitigate any kind of a contact or thermal resistances associated with the heat transfer between the slurry and the air side of the cooling system. And also note that the slurry was in the natural convection, meaning we had no stirring mechanism in the subcooled liquid in order to be able to make it work effectively. And when we went through the optimum design of the heatsink, and we saw that there's a point of optimum associated with this heatsink, and the thermal resistance is about 1.15. And the analytical model that we always go through showed that it is consistent with our calculations, so we could now go to production and produce the part that was designed. And you can see this is a traditional effect that we see as you increase the number of fins. You don't necessarily get an improved performance. There is a point of diminishing return, and you're gonna choke the heatsink with the additional fins, and it's not going to work effectively. So the short of the message is there is a point of optimization that we have to go through in order to make sure that the design, the liquid side as well as the air side is optimal. So the diffuser had to be designed in such a fashion that it's going to meet the pressure requirement that we had for the fan, and also the duct, the whole system, and the whole intent of this diffuser was to make sure that we are minimizing any kind of a mixture of the ambient air with the system as much as possible. We do the pressure drop calculations about 1.85 Pascal, and the duct work that you see here that would carry the air back and forth had a pressure drop of about 3.75 Pascal. That combination of these two and the fan curve that we have for the fan that we had chosen and the system curve give us the adequate flow that we need this is delta P, this is volumetric flow rate, adequate flow that we need in order to select the right fan and design it accordingly. You see some pictures of it and the temperature variations and so forth, and here's you see the ATS sensors that are placed in here to measure the airflow. You can see the little fog that is created as a result of the mixture of the ambient air with the coolant, and you can see that we're reaching the level that we want based on the flow requirement. And here you can see that we have 5 CFM, or about 350 linear feet, 1.5 meters per second, just about 1.7 meters per second of airflow through the system. And although this doesn't look like much difference, but remember the intent was to minimize the pressure drop in such a fashion that we can get adequate flow and minimize the noise as much as possible. So when you look at the, if my page advances, when you look at these two, this is the old design that you see that there's some sharp bends effectively, and then the optimum design as a result of our CFD to see what is the best design to minimize the pressure drop and make sure that the diffuser and the duct work are in such a fashion that the least amount of delta P is created for the fan to work and operate effectively. Oh, sorry, this new picture is not coming out, but The old design was like this, and the new design, you got a sense of it, what it's going to look like here, and you saw the picture earlier on in the onset of the presentation. I apologize for this picture not being available. So the desiccant was a critical factor of the whole design. Remember, we had some requirement for visibility and lack of frost. Frost has two effects, both blinding the site and also potentially impacting the integrity of the cells. So the objective of the desiccants is to remove the humidity from the air and prevents a frost buildup on the samples and the components. So the molecular sieve for the desiccant that we chose was reduce the dew point of air down to minus 84 degrees C, retain 24% of the own weight in water, which is very good, and is easily regenerated in an oven. So we can put it in there and dry it up and then reuse it again. That helps us quite a bit with the design and mitigating the cost. As I mentioned before, we can always use a dryer, not a hair dryer, but the air dryer, that you can extract the humidity out of it and put it back into the system. That's always an option if the budget of the project allows it, and the noise constraints. You can see some mechanical characteristic of the molecular sieve calculations that we had to go through to make sure that it is going to meet our requirement. The volume of the desiccant that was required and the 25% estimation of mixing. You can see the levels that were available to us to select for the duct and the desiccants and so forth, as far as the surface area is concerned. And there are numerous options that we could have chosen, and you can see some significance differences between the pressure drops. It's a monolithic honeycomb structure developed by Grace Davison, extrusion formed, fast absorption in high velocity, easily handled of solid pieces, and very brittle. And the inexpensive version of it is about $8 per pound, readily available, high crush strength, and must be contained in an enclosure so we can take advantage of it. You can see the mesh that this thing is enclosed in. But to take a note of the pressure drop, both experimentally obtained, and these do make a difference in your design depending upon the airflow rate requirements that you have, as I showed before with respect to the system curve and the pressure. So every resistance across the path of the flow, you want to be able to minimize it in order to make sure you get the best. And then applications, which application gives you the most effective value for your process and your work. So the final testing, this was actually put into production and delivered to our client. Data logged with Fluke Hydra and ATVS 2020. ATVS 2020, as John mentioned, is a hot water anemometer that measures air velocity and temperature. You saw the sensors earlier on. 12 thermocouples were used to measure different temperatures on the system that were critical. You can see the heat exchanger sticking out on the side, where the other side of it was embedded into the slurry, and we use the velocity sensors to monitor the volumetric flow rate and make sure that our calculations that we've done a priori meets the design requirement. So the good news was the final result was that we met the requirement, actually exceeded the expectation of the design. And remember, the objective was this red line here at minus 70 degrees for 6 hours. And as you can see here, we were able to go to about minus 75 on average and maintain over 7 hours of steady temperature. Beyond 7.5 hours, or possibly 8 hours, we noticed that the change is made and the sample may not work properly. But we managed to exceed by something like 20% the design requirements, and by about almost 10% the temperature requirements for this design. So upfront calculations, upfront design process, and then verification as we go through. As you've heard me say in other presentations, we always have to have two independent solutions. You saw examples of analytical modeling and computational. You saw examples of analytical modeling and experimentation. Combination of the two enabled us, and hopefully you guys, when you go through the design, to develop a system that's going to meet your requirements right the first time and on time, and that's very important. So medical industry shares many common challenges with the electronics cooling field. The laws of thermodynamics do not change because of the fact we went from a telecom market to medical. We went from medical to energy. The laws of physics don't change, and all it is the boundary conditions, the way the equipment are packaged, the materials that are used are different. But the laws of physics are laws of physics. If we understand the laws of physics and we can use it effectively, we can have a very successful solution. Classical electronics cooling deal with a maximum allowable temperature only. Medical devices often have much tighter temperature goals, such as isothermal surfaces and repeatability, as we've discussed it multiple times. It is also important to consider the thermal solution even earlier in the design stage and have 2 or 3 independent solutions as we talked about it. You saw the benefit of it. This was a case study that we had done, that we went through the whole process. The important thing is, as you're dealing with medical equipment, you're dealing with human factors, you're dealing with people, you're dealing with potentially animals and so forth. The errors are not tolerable. It's not like your data center went down and you lost functionality for 2 hours. If your design ends up hurting somebody, you have a possibility for a lawsuit. You have a possibility of a huge financial risk that may be awaiting you. So what we strongly suggest as you're going through the design, whether it's a biomedical, any kind of engineering design, you have to have 2 independent solutions. Just for the sake of completion, let me just say what I mean by 2 independent solutions. We have 3 options for analysis. We have analytical modeling, paper and pencil that John described it. We have computational, we have experimental. So 2 independent is you do the analytical modeling, and depending upon your problem, you either go with experimentation or you go with computation. You don't pick up the results of the analytical model and plug it into your computational model, or the results of your experiment put in your computational model. Excuse me. The intent is somebody will do the analytical model, somebody do the computational model, you put it together, they have to match within 15 to 20% worst case. If they are, the likelihood of the solution being accurate for the boundary condition that was given to you and the problem statement that was given to you is very high. If you're not within 15 to 20%, start all over again. Something is astray and you got to fix that. So with that, I thank you for your attention. I hope the information was conveyed in such a fashion that you could benefit from it. Remember that ATS is here to support and help you. We are one company with a total solution, and our expertise in this area is pretty expansive, and we can help you in the variety of applications that you may come across. But I thank you for your attention, and if we can be of any assistance, please give us a note, and if you have any questions, I'll be more than happy to entertain. Thank you.